Should be good to live. Hello, hello everybody. Welcome, welcome. Howdy, howdy. We will be getting started in just a moment. We just first have to get some people in here before we start. Welcome, welcome everybody. Howdy, howdy. Hope my audio's okay. Thank you for the heart thing. No, this isn't my paper. We're just reviewing a paper that I found on the archive today. No, I'm not one of the authors. We're reviewing this paper. We're not, you know, writing a paper or going over my own work. How could tachyons be heavy if they're proposed to be fast and light? Well, that's what we're going to find out. I have no idea. I have absolutely no idea. Just want to make sure that everything is up to go. I think that we'll be good to go. We're just going to give it a few more minutes, see if we can get some more people in here before we start, and then we'll jump right in. So feel free to stream in, and we'll have some, hopefully. So I haven't read this article yet. So we'll see. Since no one is here, I want to ask you a question. What's your idea of the explanation of creating objects in different dimensions? I don't understand what the question means. I'm sorry. I'm really sorry. Yeah, so if you're coming in on TikTok, make sure to like the live. If you're watching on YouTube, or if you want to be watching on YouTube where the audio quality will be better, head on over to YouTube. My name on YouTube is @BlitzPhD, same name as it is on TikTok. You can go watch there. Probably better that you watch there, to be honest. What do I do for work? I'm a researcher. I do physics and mathematics. It's my day job. Welcome, welcome. We're going to be starting once we hit 200 viewers on TikTok, and then we'll be able to jump right in. So feel free to stick around. Shouldn't be more than a few more minutes. Actually, I'm going to go fill up my water bottle, so keep the chat going. Yeah, make sure that they hydrate. All right, we're back. Welcome, welcome. Yep, I'm a full-time nerd. What's the live going to be today? We're doing our peer review. And when I say peer review, what I mean is reading. So, interestingly enough, this paper is written by somebody who has a bit of a reputation. I'm going to try to not let it color my view of this paper, but it should be interesting. So stick around. It might be a relatively short live, maybe about an hour. Then I'm going to play some Marvel Rivals with my wife because we've been doing that. It's good old time. Who do I play? I've been playing a lot of Magic, but when I need to, I can switch over to Hela. I've also played some Storm, but I kind of just started, so I'm new to the game. Right. All right, so we may as well get started now. So let's start with the paper. So this paper is called Black Holes Rule Out Heavy Tachyons. The authors are Mark P. Hertzberg, Abraham Loeb, and Aidan Morehouse. Now, for those of you who are in the know, Abraham Loeb has a bit of a reputation. He has a bit of a reputation of being a little on the, I don't know, he entertains ideas that not everybody would entertain. He got into the news, a few years back over this whole aliens at the bottom, or the whole alien particles at the bottom of the oceans thing. So this is all to say, he writes very perhaps contentious papers. I can't say that he does bad physics. I mean, he's at Harvard. He's a highly respected physicist. He just has a reputation. So let's try not to let that color our reading of the paper. Let's take it in what it is. So let's start with the abstract. So we present direct observational constraints on tachyons, particles with group velocity. So they're going to explain. Tachyons are particles with group velocity greater than c in a vacuum in the Lorentz invariant theory. Since tachyons may so by the way, tachyons are particles that go faster than light. That's what a tachyon is. That's the idea. Since tachyons may have no direct couplings to standard model particles, meaning that they don't interact with like photons or they don't interact with like neutrinos or whatever, the most robust and model-independent constraints come from gravitational effects, especially black holes. We compute the Hawking radiation of tachyons from black holes, finding it to be significantly enhanced in the presence of heavy tachyons. For a black hole of mass m and tachyons of mass little m with g degrees of freedom are basically the different ways that you can characterize a particle, but it's still having to be the same particle. Think of like spin up and spin down, that would be 2 degrees of freedom, right? Anyway, sorry, actually, that's not quite right. It'd be like, well, yeah, something like that. Or oscillating up and oscillating sideways, 2 degrees of freedom. Anyway, right, so for a black hole of mass m and tachyons of mass little m and g degrees of freedom, the black hole lifetime is found to be 192 pi times h bar, that's reduced Planck's constant, times the mass of the black hole divided by the number of degrees of freedom times the speed of light squared times the mass of the tachyon squared, which becomes doubled if you're talking about fermionic tachyons, apparently. We're probably going to get into that and as to why. This implies that the observation of black holes of a few solar masses with lifetime of several billion years rules out tachyons with a mass greater than 1 billion gigaelectron volts. This means there cannot exist any tachyons associated with unification scales or quantum gravity. So while there already exist theoretical reasons to be skeptical of tachyons, our work provides a complementary direct observational constraint. So look, the point is maybe we're wrong. Maybe tachyons can exist that have mass. And so they're going to put a constraint on it. Is my mic quiet? How's my mic, everybody? I can turn it up if that's needed. How's that? Is that a little bit better? Better, worse? Okay. All right, let's stay here. Great. I just want to confirm with YouTube that the audio, that the audio is okay. YouTube, can you hear me all right? Okay. Right, so shall we read? All right, so let's just start and I'll just explain as I go. So, it's a fundamental issue to identify the family of types of particles that exist given the constraints of relativity. Lorentz invariance says that there are 3 basic types of particles allowed. Massive particles that always travel at the speed less than the speed of light, v less than c. Massless particles that always travel at v equals c. And tachyons that always travel at a speed greater than c, c being the speed of light. All known particles fall into the first 2 categories. The third category of tachyons is the subject of this work. Okay, fine. Here we'll be interested in honest-to-goodness tachyons, particles whose group velocity is greater than c defined with respect to a stable vacuum, as opposed to some contexts which focus on classical field vacuum instabilities. The field theoretic description is clarified in Appendix A. There is a statement about tachyonic instabilities. This is a thing that exists in the standard model of particle physics. That's not what they're talking about. They're talking about genuine tachyons, particles that move faster than light. So there are theoretical reasons to be skeptical of their existence, namely that faster than c propagation could be used to send signals outside the light cone, and then 3 observers that are highly boosted relative to each other. Highly boosted just means that one is moving fast, one is moving very, very quickly relative to another. Right, so 3 observers that are highly boosted relative to each other could find ways to send a signal from observer A to C, or A to B to C to A, and have it arrive before it was sent. So, the time travel, right? Such behavior may lead, or at least backwards time communication. Such behavior may lead to paradoxes of causality, although there are works challenging this, such as reference 2. We should actually go take a look at what that reference is. It might be interesting. Oh, I read this, but we actually reviewed this paper. We reviewed this paper last year. So go watch that. It's somewhere in my YouTube where we reviewed that particular particle, or that particular paper. It was really fun. Right, anyway. On the other hand, as we will discuss shortly, not all momenta are allowed for tachyons. Momenta being the plural of momentum, by the way. So they cannot be localized fully. This means that they can only be used to send signals with finite precision, although we can carry an open mind to their existence and look for direct proof of their falsification or otherwise. So this is what we're going to study. Dream of Dawn, I know who you are. The paper is Black Holes Rule Out Heavy Tachyons. We're talking about tachyons. By the way, if you want to follow along on the paper, the archive link is over here. So just type in this number, archive, or type in this code, archive 2501.11606v1. You'll find it, and you can follow along. Of course, this has some sensitivity to the types of interactions that the tachyon has. If the tachyon has significant interactions with standard model particles, we may expect it to be especially easy to produce signals into the past and various paradoxes. So essentially, if the tachyons can interact with photons, then you could use a photon to encode a tachyon, use the tachyon to send a message into the past, and then decode it with a photon, and that would be a problem. Furthermore, we may expect to have already found evidence for tachyons through various precision laboratory tests or particle detectors of various kinds, i.e., if they did interact with the standard model of particle physics, we would have expected it to be found. By the way, for those who are interested, this article came out a week ago. Quite new. That's why we're reviewing it. It's fresh off the press. In fact, the opera experiment, you guys might remember this if you're old enough, about 14 years ago, they claimed to have detected faster than light neutrinos, but then they found out that it was a technical issue. So that was the opera experiment. In fact, as we will discuss shortly, tachyons can have an energy that is arbitrarily small, so there is no energetic barrier to producing tachyons in the laboratory. So what this means is that generally, if you want to produce a particle like a Higgs boson, this is the thing found in 2012 at the Large Hadron Collider, the Higgs boson has a large positive energy, a large positive mass. And so what that means is that in order to make it, you have to put a bunch of energy into a small place, so it's generally pretty hard to do. But the claim here is that the energy that a tachyon has, unlike a Higgs boson, which has some large amount of energy that it has as its minimum, tachyons could just in principle have an arbitrarily small energy, so you could always make them. So if they did interact with the standard model of particle physics, we kind of expected that we would have found them already, right? So that's what they're saying here. On the other hand, it is possible that tachyons interact with regular matter in the most feeble way possible. This means only gravitational interactions, as gravitation is universal, so this is the one interaction that is unavoidable. In this case, the possible theoretical problems and direct observational consequences would be reduced. So this is just saying, look, gravity applies to everything, so it would apply to tachyons. If the interactions are only gravitational, then we must find other more indirect ways to have observational consequences. One possibility is to turn to black holes. Since observations show that black holes exist, contentious amongst flat earthers, and are long-lived, meaning that they live, for billions, trillions of years, then tachyons must be compatible with this. Classically, we can inquire as to whether tachyons can escape a black hole, which seems plausible given that they travel faster than light. However, we first show that from the point of view of a distant fixed observer, even tachyons do not escape as they asymptote towards a null geodesic as they approach the horizon, just as regular massive particles do. They're going to hopefully explain this in more detail mathematically, but we'll get into this. Quantum mechanically, however, tachyons can escape black holes. We compute the Hawking radiation of tachyons, finding that for heavy particles, the flux is dramatically enhanced compared to standard Hawking radiation of photons. That's interesting. That's the important piece. And that's what they're going to use to come to their conclusion that they can rule out massive tachyons. This leads to black holes evaporating quickly if the tachyon is sufficiently massive. We use this to place a direct observational upper bound on any tachyon's mass, which is super cool. This is a really neat idea for a paper. I wish I had thought of it. It's completely theoretical, but it's the kind of thing that uses really good creative juices. Robert, thank you for the $3. I appreciate you on YouTube. The outline of our paper is as follows. Okay, this is how all physics papers go. You're going to have an introduction, and then at the end, they're going to say the outline of our paper is as follows. In section blah, we do X, blah, 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 blah. Right, so in section 2, they're going to review and clarify some basic properties of tachyons, probably useful for this peer review. In section 3, they're going to compute the geodesic motion of tachyons in a black hole spacetime. That'll be interesting, but Okay. In section 4, we compute the enhanced Hawking radiation of black holes from tachyon emission. In section 5, we use this to determine bounds from observed black holes. In section 6, we discuss our results. And then in the appendix, we clarify the field theory of tachyons. And in appendix B, we provide more results. So this is good. This is just a good summary. Let me mute this person because they're being annoying. There we go, muted. Right. So let's talk about basic tachyon theory. By the way, where I found this is I get an email every day, every weekday anyway, from the archive, arxiv.org, where I basically get a list of new preprints uploaded to the archive, and everybody uploads their preprints to the archive these days, in the fields of general relativity and quantum cosmology, and in the field of differential geometry. So I get a list of these every day of new papers that new preprints hot off the press. So that's how I found this. I was looking through my email and found this paper. We begin by recapping the basic theory of tachyons. Some of this is well known, though some points are subtle and deserve clarification. Great, because I don't know anything about tachyons besides that they probably don't exist. Let's consider the theory of particles minimally coupled to gravity with metric g mu nu. So just as a reminder, for those who don't know, the metric is a way of describing how you can measure distances and durations in a curved spacetime. For context, let us recap standard point particles of mass m, for which it is well known that their action is kind of a magic number that basically allows you to figure out the trajectory of a particle. Their action is, and here's some notations. So the speed of light we're going to choose units where the speed of light is 1, and we're going to use a plus minus minus signature because they're, they're satanic, I guess. I don't know. How can I have the dx under the radical? Yeah, so this is a way of expressing things, but yeah, this is it's sort of squared under the radical, so it's kind of okay. Right, so the action is an integral. And so it's just negative the mass times the integral of this thing. Now this is just telling you to integrate over the path length. Are you an actual degree doc? Yeah, I have a PhD in physics. So this quantity here inside here is the square of an infinitesimal path length, and you're just adding up those infinitesimal path lengths along some trajectory. And so this is just how we can use this quantity, take its variation, meaning you just wiggle the paths a little bit, and then you set that variation to 0. So basically, what you want for the way that you figure out the trajectory of a particle through spacetime is you find the path that minimizes or maximizes, depending on your conventions, that minimizes or maximizes your action. It extremizes it. Yeah, this is a line integral. Yeah. And so what you have to do is you have to vary this thing, and you'll get an equation out, and that equation is the geodesic equation. It's the equation that tells you what straight lines are in a curved spacetime. Anyway, for tachyons of mass m, one simply has an alteration in the location of minus signs. Namely, their action is this. Okay, I mean, that's an interesting claim. I don't know why that's true. I don't know why the minus sign... Well, okay, no, I guess I do know why. Because this would be positive for a particle with mass. Yeah, so if a particle is massive, then it's traveling along time like geodesics, which using their convention means that the stuff inside the square root should be positive. However, if they want a tachyonic particle to travel along a tachyonic geodesic, then that means that they would need to have a space-like trajectory, meaning that it has the thing inside the square root without the negative is negative. So they have to add a negative inside so that you get a positive non-imaginary thing on the outside, and then you can still extremize the action. Do you only need Lagrangian mechanics for this? Well, you need some general relativity. But so yeah, this is just the trajectory that a tachyon would take. And these are just going to be space-like geodesics. So both the above actions are clearly Lorentz invariant. That's true. Furthermore, we only allow trajectories in the regime in which the action is real valued. Also true. So this means that we must have that g mu nu, dx mu, dx nu. So this is telling you about the square of the length of an infinitesimal path. We must have that that's greater than 0 for standard particles, and that it's less than 0 for tachyons. So while the former stays inside the light cone, that's what it means for g mu nu, dx nu to be greater than 0. It means that it's going in the time-like direction. The latter stays outside the light cone because it's negative. That means that it's traveling in the space direction rather than the time direction. The first variable is always time, the second variable is always space. Right. Yeah, we're measuring the path of a geodesic once we get it from the metric. Yeah, this is we have a fixed background spacetime. Right. So though both can in principle be arbitrarily close to the light cone. So you can get arbitrarily close to the light cone, but you can't get inside the light cone if you're a tachyon. You can't get outside the light cone if you're a real particle. What does g mu nu even entail apart from gravitational constant? So g mu nu captures basically how distances are measured and how durations are measured. It tells you, so like if your spacetime is curved, a given distance might be smaller here than it is over there because the spacetime is curved. No, we're talking about tachyons, Dave. Right. So for context, let's begin by considering the case of flat spacetime. So this is your normal spacetime, no gravity. In this case, g mu nu is just constant. It has a 1 in the time component, and it has -1s in the space components. And this is you can think of this as like a matrix. Each component tells you essentially how long a given direction is. So this is called the Minkowski metric, and it's written in Cartesian coordinates. So the first coordinate is t, the rest are x, y, and z. Then the above pair of actions can be rewritten as this. So these are the formulas now. If you just write what dx is in terms of the action or in terms of the trajectory of the particle, dx being the small displacement in a small amount of coordinate time, say, then you can actually just simplify this thing using this metric, and you just get that the action is square root of 1 minus v squared for the standard particle, and it's the square root of v squared minus 1. Now, here, importantly, we're working with units where the speed of light is 1. So this v should really be thought of as a fraction of the speed of light. So in particular, if it was 95% the speed of light, you would take 0.95, square it, take 1, subtract 0.95 squared from it, and take the square root. And then you would that would give you the action. And then similarly, for the tachyon, it's just v squared minus 1. What does the integral do? It adds up the total distance or total space-time interval traveled along the path. This is closely related to the Lorentz factor, yeah. Why is there a negative sign outside the integral? That's just conventions, that way then you can minimize it. Had they instead chosen a different convention, then you would have ended up maximizing. Yeah, so v is dx dt, it's the particle's velocity. Nothing scary happening here. Why is the dt in front? That's just a physicist's convention. It's just you can put it on the left, you can put it on the right, it doesn't matter where. It's an integral of this whole thing. And m stands for the mass of the thing here, by the way. Right, so from the action, we can readily deduce the particle's energy and momentum. So you can figure out the particle's energy and momentum just by... So the way that you derive energy and momentum is by figuring out by observing that there's a quantity that doesn't depend on the time and doesn't depend on the location. And so then you get conserved quantities, which are derivable from the action. This is Noether's first theorem. And the way that you get them is a little bit involved. It involves doing a variation of the thing and then taking the time derivative and setting it equal to 0. Or showing that the time derivative of a particular variation is 0, and that shows you that the thing that you're time varying must be constant. But regardless, we end up with a formula for the energy and a formula for the momentum. P stands for momentum. Now, this is just the standard formula for energy. This is just gamma times mc squared, right? The standard formula for relativistic energy, gamma mc squared, where gamma is the Lorentz factor. That's what this is. It's just the c's aren't there because we set c to 1. We chose a set of units where it's 1. And then this is the relativistic momentum. Again, it's just gamma mv, standard relativistic momentum stuff. Now for a tachyon, it's almost exactly the same. It's just instead of 1 minus v squared, it's v squared minus 1. What does the term action mean? Action is just the name of an integral that when you vary it, it gives you your equations of motion. That's all it is. Generally, you can kind of think of it as like some sort of weird version of energy, but it's not really. It's just some... it's a quantity that you want to extremize, or it's a quantity that particle trajectories must extremize in order to satisfy their equations of motion. That's all action is. Action, like S stands for action for whatever reason. What if I just died on the live stream, just like choking to death? By the way, for those who are just joining us, the paper is called Black Holes Rule Out Heavy Tachyons. And if you want to follow along, you can just type in this archive, ARXIV, 2501.11606 into Google and you'll find it. Anyway, let's continue. Gabriel, you can do it. I believe in you. By the way, if you're watching on TikTok, make sure to like the live so that we can get more people in here. Want more people to learn. That's the goal. Anyway, so we can then use the energy and the momentum to solve for the mass, essentially giving us an energy-momentum relation. So the standard E equals mc squared tells us about a relationship between the mass and the momentum and the energy. This is the energy-momentum relation. I can watch this on a normal platform like YouTube. Absolutely, you can. Yeah. Can you decrease the sound a little? People were yelling at me to increase it. All right, let's decrease a little bit. And then the energy momentum relation for a tachyon, on the other hand, is p squared minus m squared, which is interesting. Hey, there are numbers here. That's a 2. That's a 1, and that's a 7. There are numbers, right? Increase the sound a little. Oh, okay, yeah, sure. Right, this is also streaming on TikTok, by the way. We have a few hundred viewers over on TikTok. Right, so here, the p without the bold is just the size or the magnitude of the momentum vector. By the way, if you're watching on YouTube, make sure to smash that subscribe button and click that like button like your life depends on it or something like that, right? And if you're watching later, make sure to like the live, I butchered that. If you're watching later, make sure to like the video or something, right? Is this degree level? This is PhD. This is research. This is a research paper. Right. So the above formulas demonstrate that the allowed domains for each type of particle is complementary. Namely, standard particles exist within the domain V is less than C, while tachyons exist within the domain V is greater than C. And it should be emphasized that within their respective domains, the corresponding energy, momentum, and action are all real valued quantities. Like, there's nothing imaginary here. There's nothing negative here. Everything is just real. It's all totally well defined. Welcome, Indranil. I'm sorry it's banned over there. Oh, we have a plot. We plot the momentum for motion along some axis versus velocity in figure 1. Let's look at this plot. We love plots. What if this is just a solution that describes particles outside of our light cone? No, this is a solution that describes particles moving outside of their own light cone, right? So we have momentum versus velocity. The standard particle case is in blue, and the tachyon case is in red. So we have momentum on the right. So let's just look at the positive momentum. So for a standard particle, as the velocity approaches light, momentum increases without bound. As the velocity for a tachyon approaches the speed of light from above, the momentum also increases without bound, but you can get the momentum down very, very close to 1 by making the velocity even faster, which is interesting. And that should be fairly straightforward. If you just make the momentum for the tachyon like 1 billion, right? If you make the speed like 1 billion, then this just becomes m. And the momentum here is measured in units of mc, so that's why. The tachyon escapes the light cone because it's a tachyon. Right. We note that the allowed domains of energy momentum differs between standard particles and tachyons, as the energy for a standard particle is always greater than or equal to its mass, and its momentum is always positive. And the energy for a tachyon is always greater than or equal to 0, and the momentum is always greater than or equal to its mass. So that's interesting. Is this PDF free? Absolutely. Just type this into Google. Type this into Google. ARXIV : 2501.11606, and you will find this first link. It's free. It's freely available, published online. How does momentum decrease when you increase velocity? Well, that's what the equation says. That's just what the equation says. And they derived it using the action principle, so that it's just right. It's just what the momentum is for something following that action. Anyway, The restrictions that the magnitude of the 3 momenta of a tachyon obeys p is greater than or equal to m is seen in figure 1. So see how the red line is always above 1? That's what they're referring to here. It is important to note that this statement is closed under Lorentz boosts, i.e. for a tachyon with momentum greater than or equal to m, it is guaranteed to have a momentum p prime greater than or equal to m after a boost, although it can sometimes switch from the upper right branch to the lower left branch. So you can have something red switch to something red over here. It'll never ever escape from being on one of those lines though. This can be checked from the velocity addition rule of special relativity for collinear motion, which I guess still applies. V prime is equal to v plus u divided by 1 plus vu, where u is the boost velocity with u is less than 1. So if you boost the frame, basically if you look at what's happening from like something that's from the perspective of something traveling near the speed of light. No, the blue line is a standard particle. It's not a tachyon particle. The red line is a tachyon particle. If you apply a boost, so you change the reference frame by applying a boost, then the new tachyon's velocity is v prime, whereas the old one is v. So v and v prime is the tachyon velocity before and after the boost. Conversely, tachyons can have arbitrarily low energy. That's very strange. Only bounded by e greater than or equal to 0, and this statement is also closed under Lorentz boosts. So this is to say, tachyons can have an energy that is as close to 0 as you want, which is very weird. The e goes to 0 limit, which is also the p goes to m limit, occurs for tachyons with speed approaching infinity. So what's weird is that the closer the tachyonic speed gets to infinity, the lower the energy. And that's kind of weird, right? But whatever, that's what the math says, and the math tells us what the physics does. So if these things are real, that's how they behave. We note that this construction does not permit negative energy tachyons, nor is there a basic type of vacuum instability. Formulating the theory with a vacuum instability is sometimes associated with tachyons in the literature, and a distinction is clarified in Appendix A. Nevertheless, if there were direct couplings to standard model particles, one could imagine readily producing such low energy tachyons in various processes, which is itself a kind of instability. By only coupling gravitationally, as we do in this work, this is radically suppressed. So all they're going to do is they're going to say, look, things would be bad if these tachyons were able to interact with, say, photons. So instead, we're going to pretend that they don't. And they probably don't, because they probably don't exist. Sounds like the tachyon would basically be no energy in my light cone. I don't understand what that question means. This is theoretical physics, not hypothetical. This is real physics, just applied in a theoretical scenario. We note that since the momenta is bounded by p greater than or equal to m, then within the quantum theory, one cannot form arbitrary types of wave packets. That's interesting. So you can't make wave packets of whatever kind you want because the momentum, which is related to the wavelength of the quantum wave, can't get arbitrarily small. The momentum has to be bigger than a certain amount. In particular, one cannot build standard localized wave packets, as this requires the use of all momenta. Yeah, so this is a good point. If you want to localize, so if you want to build a wave packet, which is just like a kind of, you can think of it as like a single particle. If you want to build a wave function for like a single particle electron or a single particle Higgs boson or whatever, then you have to be able to add up a whole bunch of different waves together so that they cancel everywhere except at one place. And in order to do that, you need to have access to all possible values of momenta, including the ones that are close to 0. But if you don't have that, you can't localize a tachyon, you can't localize your particle, and because the tachyons have a limited upper or have a lower bound on the momentum, they can't get down to 0 momentum, you won't be able to build whatever wave packet you want, which means that you can't localize them, so they'll be kind of spread out. And that's what they're going to say here. Hence, tachyons within the quantum theory are somewhat delocalized. This means that while they can send signals, there is some imprecision. Some have argued that this means there is no direct breakdown of causality, although there remains forms of non-locality. A full exploration of this issue is beyond the scope of this work. In any case, the classical limit is still unambiguous, faster than C propagation, and this is true in all frames of reference. Cool. Do tachyons have spin? In this paper, they're not considering spin whatsoever, although that would complicate the matter. Right, all right, now we're going to talk about the behavior of tachyons in a classical black hole spacetime. It is an interesting question as to what extent a particle can enter or escape a black hole. I agree. This is like a linear type of momentum. This is translational momentum. From the point of view of a distant fixed observer, standard massive or massless particles treated classically do not, in fact, enter a black hole as they undergo arbitrarily large time dilation, causing them to appear frozen. This is just this idea that if you're watching from really far away, the people close to a black hole freeze before they fall in. We now check on corresponding classical behavior of tachyons before turning to the quantum behavior in the next section. So we're going to start with a Schwarzschild black hole of mass m, which is the easiest and nicest black hole, which has metric in terms of radius r and time t. So here's the metric form. So remember that before we had 1, minus 1, minus 1, minus 1. Here it's a little bit different. So if f was 1, then we would have 1 in the first slot, we would have minus 1 in the second slot, and then we would have the third and fourth slots. Those are captured by this d omega squared term, and this is just spherical coordinates. You could write it in Cartesian coordinates, but this is a spherically symmetric thing, so it makes sense to write it in spherical coordinates. That's all that's happening here. So in this case, if f of r was 1, this would be 1 minus 1 minus 1 minus 1, but f is just telling you how the black hole actually warps the spacetime. Yes, f isn't exactly the gravitational field strength. It is closely related to the gravitational potential. So here, f is just this function. It's this quantity here is the Schwarzschild radius, 2gm. So in r, so 2gm is a distance. It's twice times Newton's constant g times a mass m. If you are at the radius of 2gm, the Schwarzschild radius, then this f of r is equal to 0. And when that happens, you have 1 divided by 0, and that's when you have an event horizon. You have a 0 out here, and you have a 1 divided by 0 out here, which means that you have some sort of horizon going on. Anyway, I don't know why they wrote it this way. They could have just plugged it in here, and it would have been easier to see. Neither here nor there. Anyway, they're going to consider radial motion of a particle, either towards or away from a black hole, with d omega 0. So they're just imagining a particle moving towards or away and not moving in any angular direction. That's why they can set d omega to 0, because that implies motion in an angular direction. So then you can do the exact same game that they did up here, where you write down what the action is. It's just a little bit more complicated. Why is the Schwarzschild metric? The Schwarzschild metric is the simplest metric for a black hole. I would actually think that maybe the next step would be to do the same thing for a Kerr black hole, and you would expect to get basically the same thing. Anyway, so the action in that case is given by this. So they've kind of encapsulated the action in two different ways. They've just introduced a symbol epsilon that is either +1 or -1, so then they can write down a single action for both different types of particles. So here we have epsilon f of r. So we have this term here. Then we have, so that's the dt part. That's the 1. That's that 1 there. And they're integrating over dt, so that's how I know. So this is the 1 here. And then this part is the minus v squared. It's not minus v squared, because the part that involves the motion, the dr, so you would take dr, you would divide it by dt, and then take the square root. That is f of r to the -1. That's why there's an f of r to the -1 here, and then you multiply it by the velocity, because dr dt is the velocity, which is what it says there. So here we have that, like I said, they're introducing a unified notation. So epsilon is +1 if you're talking about a standard sublight particle. Epsilon is -1 if you're talking about a tachyon. All it does is it flips the sign inside and it flips the sign outside. So the action is still fairly straightforward. One can still compute it. One can still vary it. Not a super complicated thing. And then, since the spacetime is static, the particle's energy is conserved. So there is an energy conservation here. There will not be a momentum conservation, but there will be an energy conservation. From the action, there will be an angular momentum conservation, by the way, but that's not relevant. From the action, we can readily derive the energy to be this. This is the energy formula. Again, epsilon is +1 when you have a normal particle, and it's -1 when you have a tachyon particle. And now, I guess they're just going to use this to solve for the trajectory. Using v of r equals dr dt, so we know that v of r is dr dt, and separation of variables, so this just basically becomes an equation of motion, or an equation, right? The energy E is just some constant. V of r is dr dt, so you can rearrange the equation to solve for r of t. You would multiply both sides by the denominator, you would divide by e, you would square it, then you would subtract off a bit, and then divide through by e times f of r to the minus 1, and then you would take the square root again, and then you would be left with a differential equation, dr dt equals something horrible. And it turns out that you can then just integrate it and find the actual solution. Unfortunately, it will give you an implicit solution, because integrating that equation would be horrible. The epsilon is just multiplication. It's just multiplication by plus or minus 1. So what they find is that as a function of r, so you integrate from r1 to r2, so as the particle goes from r1 to r2, the amount of time passed will be this value t. So all you have to do is take this integral. That will give you a certain amount of time. And so that will be the amount of time that passed for the object moving from r1 to r2 along its natural trajectory. Yeah, we can reorganize this to express the time taken for a particle to travel from some radius r1 to another radius r2 as this. Great. Note that the integrand diverges as we approach the horizon. So let's go note that. Let's actually take a look. So as we get to the horizon, f of r goes to 0. Remember, when little r, this is the distance from the center of the black hole, when little r is equal to 2 times g times m, which is the horizon, we get that f of r is 0. But if you plug in 0 into this formula, you get that 0 minus 0, and you're dividing by that. So the whole thing goes to infinity. dr is just the distance away from the center. It's the coordinate distance. So think of it as like square root of x squared plus y squared plus z squared. Right. Note that the integrand diverges as we approach the horizon, where f goes to 0, and this is true for 1, standard massive particles with epsilon equal plus 1, and 2, massless particles with m equals 0, and 3, tachyons with epsilon equal minus 1. So the point is that this is true in all cases. The integrand diverges in all cases. That's an interesting observation. To quantify this further, suppose R2 is close to the horizon. So R2 is close to the horizon. For particles that are outside the black hole, so this would be for a particle that is the final stage of the particle is near the horizon. For particles that are outside the black hole initially at R1, but are heading inwards, so they start off far away and then they end up close, we write R2 is, say, 2 gm, so that's the event horizon distance, plus some small amount, delta r. And delta r is positive, and let's just say it's just a small amount, so it's like 1% away from the event horizon. Then the integral can be expanded in delta r, so pull out your nifty Taylor series expansion, and you can just actually integrate. You can actually do this integral by expanding in delta r, which is kind of nice. You can actually just do it. You get a logarithm, you get some other stuff, and you get a delta e, which is a subleading piece. No, delta r is delta r is the variable here. It's just a small amount of r, basically. So in this case, the amount of time it takes to get from very far away from the black hole to very, very close to the black hole. Question. Where can we find this paper? Just punch this into your Google machine. Archive ARXIV : 2501.11606. Right, so we have that the time taken to go from far away to very, very close to the horizon is going to be this. It's going to be this quantity regardless of, well, yeah, so there's this logarithm term. So if R1 is how far you start off, but then you divide it by some tiny number. So this natural log is going to be quite big. So as you get closer to the event horizon, the amount of time it takes to actually get there, the amount of coordinate time rather, goes to infinity. However, oh, you're talking about the capital delta. We're not there yet. And so this is and then you can add in R1, which is just your starting point. Subtract off the final point. And then there's a little, like a subleading term, and then an extra subleading term, delta E. Now, they're probably going to explain this. Where the leading term is the same for all three types of particles. Only the subleading piece, delta E, differs between the types. When the energy is very, very high, much, much higher than the mass, then delta E looks like this. So delta E, it's just another subleading term. That depends on the mass and the energy. But importantly, the leading structure is always the same. It'll always approach an infinite amount of coordinate time to get to the event horizon. But importantly, this delta E enhances the time for standard massive particles, or it decreases the time for tachyons. That's the important bit. So it's just positive if you have a massive particle, so it takes longer to get to the event horizon for massive particles, and it takes less time to get to the event horizon for tachyons. But in the case where delta R goes to 0, we see that the time taken diverges logarithmically due to the leading universal term. That's this guy here. Oh, stop it. So from the point of view of a static distant observer whose clock reads time t, no particles enter, including tachyons. So tachyons can't enter black holes, even though they're moving faster than light. Now, for particles that are inside the black hole, then only in the case of tachyons can we consider the possibility of them moving radially outwards, as they exist outside the light cone. True. Do I ever pause for questions? I read questions during it. Yes, so tachyons are things that are supposedly moving faster than light. So these are the things that we're studying here. This paper is about black holes rule out heavy tachyons. So we're studying this question, exactly. We're studying, can there be heavy tachyons? Nevertheless, the above divergence persists, and we have the same logarithmic divergence in escape time. So if you have a tachyon inside, it still can't escape. Hence, all three types of particles do not enter or escape black holes from the point of view of a distant observer when treated classically. So you will never find, even if tachyons are real, if you're watching a black hole from far away, you'll never find a tachyon starts off inside the black hole and then leaves the black hole, even though it travels faster than light. So, now we're going to get to the juicy stuff. We're going to talk about enhanced Hawking radiation. We're okay. Right. Be for real, what do you use this for? I use this to learn about tachyons. This is theoretical physics, bud. Quantum mechanically, black holes radiate. Yes, we know this. Article link. Type this into Google. ARXIV : 25.01 or 2501.11606. Quantum mechanically, black holes radiate. As Hawking showed, the temperature of a black hole, by the way, this is Hawking radiation that's being talked about. As Hawking showed, the temperature of a black hole is in geometric or in natural units. It is 1 divided by 8 pi times Newton's constant times the mass of the black hole. That's the temperature. We now wish to apply this to compute the output power of particles from the black hole for tachyons. Okay. Yeah, this is in Kelvin, yeah. Here we follow a leading approximation in which we use thermodynamic results of flat space, as the equivalence principle ensures that the flat spacetime is locally flat, or that the spacetime is locally flat near the horizon, although this is not precise for particles whose de Broglie wavelength is comparable to the horizon size. As is the case for Hawking radiation of massless particles, it is more accurate for heavy tachyons whose momentum is large, p greater than or equal to m. Basically, all they're saying is that they're going to use an approximation, which should be fine for tachyons because they have a big momentum. This is an equation. Yeah, this is an equation. Right, so for a thermal distribution of free particles with vanishing chemical potential, don't ask me what chemical potential is, I never fully understood it, I don't think. The output power from a spherical black body can be readily shown to be this. So they're going to take some temperature black hole, and they're going to figure out what the output power is for a tachyon, given that it has a certain temperature, right? And so this is a formula that is for a thermal distribution of free particles. So you have G being the degrees of freedom, we have A being who knows what A is. A is the surface area of the black body, and 1/4 accounts for a reduction from directionality. Not all particles are heading radially. So we have the V has got to be the frequency, right? Power is proportional to the output. Yeah, V is the frequency here. So we're looking at output power. So this is something that in principle you could derive in a thermodynamics class, but I haven't done that in so long that I would have to just take their word on it. But this is the kind of thing that I think I've seen in a stat or in a thermo class, so it's been a while. Anyway, so you have the velocity, you have the energy, you have this exponential factor. It's the energy divided by, it's the energy of the particle that, or of the radiation that you're integrating over. And then you have a minus or plus 1, depending on bosons or fermions. So let's just go read their explanation here. Where A is the surface area of the black body, in this case the black hole, 1/4 accounts for a reduction from directionality, i.e. not all particles are going straight out, they could be going out at angles. The factor of V of P here, as the power is there's a factor of V of P here as the power is proportional to the output flux, which depends on the particle's speed. So if it's moving faster, you have more power output. We have included a factor of minus plus for bosons or fermions respectively, and G is the corresponding number of degrees of freedom. So that's what all of the terms in the integral mean. It is important to note that while the domain of integration for standard particles is over all momenta, the domain of integration for tachyons is the exterior of the 3-ball. P is equal to the magnitude of P, which is greater than or equal to M, as explained in section 2. So, now they're just going to describe how to carry out the integral. It's not going to take very long. So in order to carry out this integral, we first trivially integrate over angle, which gives us a factor of 4 pi out front, and it gives us a p squared inside the integral. Then we find it more convenient to integrate with respect to energy rather than momentum, so they use the energy-momentum relation, namely p dp is equal to e dE. That comes from... That's actually not trivially true. Yeah, we gotta be careful here, but... Oh, no, that is true, I'm sorry. And the velocity is dE over dP. That's true. And that's P over E. You can see that from this equation. And then P is given by the square root of E squared minus epsilon M squared. Fine. That's the momentum, and epsilon is again +1 for standard particles, -1 for tachyonic particles. And the final expression again includes the unified notation epsilon being ± 1 for standard particles or tachyons, as I said. The power output can then be written as this. So they've swapped their integration variables from momentum to energy, and now they're integrating over the energy. And this is the power output. This is the total power output from some black body with some temperature, where the lower endpoint of the integral is equal to m for standard particles, because that's the minimum amount of energy for a standard particle, and for tachyons, it's 0. So tachyons can have a minimum energy of 0. Standard particles cannot. That's going to be the difference here. In the case of tachyons, we can carry out this integral exactly to obtain the power this. So this is the power output for bosonic tachyons. You can just do the integral because you have a +1 here. And for fermionic tachyons, you can just do the integral. In the limit of light tachyons with mass significantly less than the temperature, this reduces to the standard result of massless particles. So if you have very, very light tachyons, then the power doesn't care if it's a tachyon or a standard particle, right? If the mass is 0, the only place where the tachyonness actually matters is in this epsilon and in this E min. So if the epsilon, if m is 0, then E min is 0, and this term goes away. So it just becomes just normal particles. It's just massless stuff. So then you just get the standard output. Those are the temperatures, or those are the power outputs for a given temperature. Fine. However, if you have a heavy tachyon, i.e. if your mass is much greater than the temperature, then, well, now your result is different. You get a different power output. Notice that the power output for massless particles, whether tachyonic or standard, goes as T⁴, but for tachyons, it goes as T squared. And that's the important difference, right? That's super important, because if the temperature is a billionth of a Kelvin, then T⁴ is going to be so much smaller than T squared. That's the important piece. They're about to mention this. Since astrophysical black holes have extremely small temperatures, we expect to be in this latter regime. Basically, for any particle with mass T, you would expect the mass to be greater than the temperature. We see that tachyons therefore have a power output from a black hole that is parametrically larger than standard massless particles like photons by a factor of m squared over t squared. Wait, is that the number 7? Like a prime number? Yes, that's the number 7. 7 divided by 960. Yep. Look, I freak out whenever there's a 13 in a calculation. right? This is reasonable given that tachyons travel faster than light, and so intuitively they should get emitted at a higher rate. Also note that the integral is dominated by energies at the temperature. So in this limit, it is dominated by energies E much less than m. So it's going to be low energy tachyons, i.e. very, very close to infinite speed tachyons. So most of the tachyons being emitted have very low energy and correspondingly have very high speeds. Note that the speed is related to its energy by this equation here. Yeah, so you could integrate over momentum. It doesn't matter. Like, it's just a choice. Let us contrast this with the case of standard mass of particles. In this case, the above integral is not expressible in terms of elementary functions. It's a polylog. However, in the heavy limit, the power output can be computed analytically as this guy. The same leading result for bosons and fermions. So, as is well known, the emission of standard massive particles, such as electrons or protons, from large astrophysical black holes is exponentially suppressed. So it has the same t squared there, but it also goes as e to the minus m over t. And if m is much higher than t, then that is a huge suppression. Conversely, the emission of tachyons is not only unsuppressed, it is in fact enhanced compared to massless particles. So let's look at the observational bounds, right? As black holes emit particles, they will evaporate away. For a black hole of mass m, we write the power is equal to the rate at which the mass changes, p equals dm dt, and we can calculate its lifetime by integrating this equation and solving for the amount of t for the m to go from whatever its maximum value is to 0. This is how, like, you just basically take the inverse of this equation. You get dt over dm is equal to 1 over p, then you integrate both sides, and you end up with this equation. So for tachyons, we can use the above results for the powers, for the power given here. These powers. And you can just do the integral. To do so, we also use the fact that the area is 4 pi r squared, which is 16 pi g squared m squared, and the temperature is given by this. The full answer is given in Appendix B. Okay. In the low mass regime, we recover the well-known result for massless particles such as photons. However, in the high mass regime, that is particularly novel. It is the high mass regime that is particularly novel. We report both results here. So for a massless particle, this is the formula. It's a well-known formula for the lifetime of a black hole. It has this factor of 10,240. It's just there because the numbers are horrible. However, for a heavy tachyon Hawking radiation, this is the lifetime of a black hole. Notice that it doesn't depend on the mass cubed, it depends on just the mass. And that's the enhancement. So black holes are really heavy, so their lifetime is really, really long. But so if you take something and cube it, it's so much bigger than just having that thing itself. So here the results are here where we have reinstated factors of C and H for completeness. So they just reinstated those. We've also introduced O1 prefactors, A, BF, and BBF, which are just for bosons and fermions. They're roughly order 1, so it's not relevant. However, there are order 1 corrections to these prefactors when the full curvature of the black hole is considered, but in the case of massless photons, the above prefactor is known to be only off by 1.6. So for purposes of this work, these estimates will suffice. So this is an order of magnitude estimate, but it's an important order of magnitude estimate. Note that self-consistently, these two results are comparable in the crossover regime. That's good. That's good that they're comparable in that regime. Right. In the case of a single bosonic tachyon, we plot the full figure in we plot the full result in figure 2. Let's look at figure 2. So this is the black hole lifetime. So for a black hole that's 3 times as big as the sun, the lifetime depends on the mass of the tachyon. So the bigger the tachyon, the shorter the lifetime, which is interesting. But that's because you have to divide through by the mass of the tachyon in this formula. You divide through by the mass squared, rather. So the black hole lifetime versus tachyon mass, the plot is for the case of the mass of the black hole being 3 times the mass of the sun and 1 bosonic degree of freedom. The red curve is the full result for the tachyons. The horizontal green line is the standard massless case. So and then the horizontal black dashed line is the present age of the universe. So importantly, the black holes would have decayed away already if their masses were too big. Right. For the purpose of the plot, we have chosen the black hole. Okay, we already went over that. The red curve is the full result, which asymptotes the standard massless result for m being much, much less than t. The temperature given as the horizontal green curve. But decreases rapidly for m greater than or equal to t as the black hole lifetime goes as 1 over m squared in this regime, which is what we're seeing here, 1 over m squared. In the large mass regime, the expression for lifetime in equation 33 can be written this way. So basically, you can rewrite this in terms of the mass of the sun, the mass of the particle, and the number of degrees of freedom. So roughly, it's 1.4 divided by the number of degrees of freedom times 10 to the 28 years times the mass of the black hole in terms of the units of the sun divided by, or times the mass of the particle, or divided by the mass of the particle in units of GeV squared. And here the mass of the sun is 2 times 10 to the 30th kilograms. Fine. So these are just different ways of writing what the lifetime is, or writing what the mass is for a given lifetime. Now, we have observed black holes with masses as low as 3.3 times the mass of the sun, which is close to the lower mass expected for furthermore, some have lived for billions of years, i.e. we've seen black holes that have lived for a long time. This means that sufficiently heavy tachyons cannot exist. If we use m equals 3.3 times the mass of the sun, and note that some black holes have existed for over 5 billion years, the above results say that tachyons in this mass range are observationally ruled out, meaning that if those tachyons had existed, the black holes that are 3.3 times the mass of the sun would have already evaporated away. Lighter tachyons could conceivably still exist from this point of view, although still tightly constrained from theoretical arguments. A simple generalization is if we have multiple species of heavy tachyons, then the above analysis leads to this. It's just a different formula, a generalization of what we just did, where the index I labels each species. So if there are many species with comparable masses, the black hole lifetime becomes even shorter and the bound strengthens. Right. We're not going to read the appendix, it's not relevant, but let's just read the discussion, we'll call it there. The falsification of tachyon masses above 3 times 10 to the 9th GeV has implications for fundamental physics. It means that tachyons cannot play a role in grand unification, often thought to be at energies of 10 to the 15 or 16 GeV, or quantum gravity, often thought to be at energies of 10 to the 18 or 19 GeV. By combining these observational constraints with the theoretical concerns that tachyons lead to a kind of breakdown of locality, then we have reasons to suspect that tachyons simply don't exist at all. The above bound is based on known astrophysical black holes. However, much lighter black holes could exist too that are primordial in origin. The discovery of primordial black holes in the asteroid mass range of 10 to the 17 times to 10 to the 21 grams, which could potentially make up the dark matter with long-lived black hole lifetimes, would rule out tachyon masses down to about 7 to 700 GeV. So, and then there's some acknowledgements and some appendices that we're not going to go over. So this is a neat paper, and you might say that this is like irrelevant. We don't care about it. Who cares? It's just tachyons. Tachyons aren't real. But the important thing is that all of the stuff that we know about, like relativity, it only applies in the low energy regime, right? Relativity is a classical theory, and we expect that quantum gravity will take over at some very high energy level, very high energy particle level. And so you might have suspected that if general relativity is going to be violated, or theory of gravity, where we say tachyons can't exist, then it'll happen at the quantum gravity regime. But if it happens at the quantum gravity regime, then the masses of the tachyons should be huge, which they've now observationally ruled out with this argument, which is super rad. Like this is actually like a brilliant paper. It's very, very simple, but it actually tells us something that we might not have known otherwise. We might not have been able to rule out tachyons from quantum gravity. So I'm going to give this paper an A+. I liked it a lot. It was really well written. It explains itself really well. Yeah. So I'm going to, I guess I'll end the live here, but feel free to go rewatch it. If you want if you have some questions, you can feel free to leave them in the comments and I'll make sure to answer them. And I'll see you guys tomorrow for Ask a Physicist. Make sure to follow, subscribe, like the live, all of this stuff, like the live stream on YouTube, subscribe on YouTube, ring the bell on YouTube, follow